Right. Hello, everyone, and welcome to MakeLearn 360. Okay, so in this question, I want to solve a question, or I want to solve this problem to illustrate the concept of what we call the uniform varying load. Okay, so let's sort of solve the question together. So actually, we have a cantilevered beam, and this cantilevered beam AB is in so the length is 10 meter long, and then it's subjected to what we call the triangular distributed load. Okay, so the load behaves like a triangle. Okay, and then assuming or using the indicated coordinate system, determine the algebraic expression for the bending moment at a distance x from the fixed end, and then also determine the maximum slope and deflection of the beam. We should take E, which is Young's modulus, as 200 gigapascal, and then we should take I, or the area moment of inertia, as what, 120 into what, 10 to the power 6. Right, so actually this problem can best be solved if we represent these by variables. So I'm going to assume that the length is L, and I'm going to assume that the intensity is W naught. Okay, and then when we finish everything, we put the variables inside. All right, good. So now this is it. So first of all, one thing you have to understand is that there is a cantilever beam, okay, and the loading has been like this. First of all, think about this as the deflection of the load is going to behave like this. Okay, so the deflection of the load is going to behave like this. So all the time for cantilever beam, what happens is that the maximum deflection occurs at the free end all the time. Whenever you have a cantilever beam, the maximum deflection will occur at the free end, and then the deflection at the built-in or the fixed end is always zero all the time. For cantilever beam, the deflection at the fixed end is always zero. Again, the slope, so the y ds at the fixed end will always be zero. So these are the two main important boundary conditions for cantilever beams. All right, good. So let's approach this question. The first thing that you have to do to solve this question is to understand the intensity. So first of all, we are saying that the beam is being distributed, the load is being distributed. That means at x equals 0, we are assuming that the loading function w of x is also 0. There is nothing. But at x equals L, then we are calling that w of x. So that is what we are actually interested in. Okay, so that is what we want to find. But then at x equals w equals, sorry, let me put it this way. So this is x equals 0, and then at any x point in time, okay, at any x equals x equals x in any point in time, we have this wx, which is going to help us. Okay, so essentially, if you look at it carefully, you will realize that at x equals L, this w of x will be w naught. In other words, you can use proportion to say that as we move from x equals 0 till we get to x equals L, this is x equals L, that is at the end. It is exactly going to be equal to w naught. That's all. So we can equally say that x over L, by proportion, we can say that x over L is equal to w of x divided by w naught. In other words, the loading function is nothing but what? W naught over L multiplied by what? X. That's all. So in other words, if you want to find the load at any section, divide the magnitude by the length and then multiply it by that section x. That is the first step. Okay, this is the first step. Let's call this equation 1. Okay, so right now we have been able to do the first part. Now there is also another thing we have to understand. This load is a triangular load. Okay, so it will behave like a triangle. Okay, now whenever you have a triangle, the centroid of a triangle will always act at a distance 1/3 of the base. What this means is that if this is the base of the triangle, then the centroid is going to happen at somewhere 1/3 from here. Okay, so let's call this L over 3. Let's say this is L over 3. Then the entire length all the way here will be what? 2L/3. Does that make sense? 2/3L. So all what we are saying is that there is a certain point where the maximum load, so that is what we want to do. We want to come up with a load which will be maximum. And we are trying to say that the maximum load will occur at some point, and this maximum load is going to be the triangle. What is the area under the triangle? So the area under the triangle is going to be 1/2 times base times height. So this time the base is actually the length. Okay, so this time around the base is the length, and then the height is actually the W naught. That's all. And then so essentially the area is going to be 1/2 times the length L multiplied by the height W naught. So which means that the actual load or the intensity of the load is going to be W naught L divided by 2, and it will occur at L/3 from the free end. That's all. That's all. Right. So at this point, this is also one thing that we have to do. So let me clean this. I want to make it straightforward as much as possible. So whenever you have a fixed support, to be able to take the fixed support away from statics, what you have to do is you have to represent the fixed support by a reaction. So there will be a reaction, and then you realize that there is this load W naught L/2. Therefore, there will be a restraining moment. So we call it the restraining moment. Okay, there is a restraining moment at A due to the fixed support. So I'm trying to remove the fixed support. So I assume that there is no fixed support. That's why I'm bringing the reaction and the moment. This is from your statics class. Okay, at this point, I'm assuming that you are familiar with all of this. Okay, so yeah, so this is a little bit of what you are expected to know, because if you don't know this, you cannot actually solve this. Okay, right. So how would we be able to solve the moment and then the reactions? Okay, so first of all, let's solve for the reactions and then we come to the moment. Okay, so you can clearly see that there is no forces acting on the beam apart from the RA and the W naught/2, which means that if we sum forces positive in the direction, then in that case, it is going to be what? So we are looking at the statics of it. We want to find the reaction, the statics. So it's equal to 0. We can say that RA is going up, but then W naught L/2 is coming down. So essentially, RA must be equal to what? W naught L/2. That's all. So if you have been asked to find the reaction is the same as the intensity, this one. Okay, so we can now replace this by what? W naught L/2. But what is the moment? So now we are interested in getting the moment, right? So to solve for the moment is basically simple and straightforward. Okay, to get the moment, all what you have to do is to so we just have to sum moment. So let's sum moment about point A. Okay, let's sum moment about point A, and then we'll be able to find the moment. So if we sum moment about point A, okay, let's quickly do this. So if we sum moment about point A, point A, sorry, let me make this MA, so that you understand that I'm summing moment about point A. So summing moment about point A, clockwise is positive to be 0, equilibrium, right? So it's actually going to what? So if you look at the moment carefully, the MA itself is like a moment. Okay, so it will come. So but then it is counterclockwise. So it's going to be minus MA. What else? And then you can see that this loading here, which is W naught L/2, is a load. So you multiply the length of the load by what? By that distance here, which is 2/3L. Okay, so it's going to be clockwise, isn't it? So it's going to be W naught L/2, and this will be multiplied by what? 2/3L, isn't it? It should be 0. If you look at this carefully, you can say that the MA, which is the load, the moment, is going to be what? Nothing but what? W naught L squared over what 3, because the 2 will cancel the 2. So interestingly, the moment at the A, that is it, and the reaction at the A, that is it. So now we are done with the statics part. Now let's come to the strength of materials part. So at this point in time, what we are going to do is that we will cut any portion at all. So let me use another color to do the cutting. Now let's say that I decide to cut anywhere at all. Okay, if I decide to cut anywhere at all, so let's say I decide to cut this portion. So if I draw it, I'm going to sketch how it's going to be. Okay, so over here you can see that I've done a sketch here, right? Now this sketch here is nothing but what? So actually the cut here is nothing but what? The representation of the section. So this is like what I did. Okay, now when you come to this portion here, this is where the reaction will be. And what did we say the reaction was? We said the reaction will be what? So we said the reaction RA is this one, W naught L over 2. So W naught L over 2, that's the reaction. And then we said that there is a restraining moment at A, and that restraining moment MA is coming this way. Okay, so that moment is also W naught over 3 L squared, right? Now because we have taken a section XX, we can now say that let's call the whole of this distance from here to here as X, right? Interestingly, what this means is that you see that when we started, we assumed that this is a load, and then the loading okay, sorry about that. So you realize that when we did this one, we said that the load was varying in that sense, and then we were using proportion, right? We said that it will occur at a distance L over 3, isn't it? So the same thing, if we have a uniform varying load, let's call the intensity, let's say at any section. So since we have taken the section, let's call it Wx. We said that Wx will be given by what? Don't forget, we said that Wx will be given by what? W naught over L multiplied by X. So it will be W naught over L multiplied by X. That is the intensity. If you want to find the maximum of this intensity, we said that it will occur at where? At a distance which is 1/3. So in this case, this will be what? X over 3. And then the load, the maximum will occur where? At a certain distance, assuming to be here. Okay. So in this case, the load is going to be the area of the triangle, which is what? Half. So half times base times height. So the base is X, and the height is what? The intensity, isn't it? Which is going to be what? W naught over L multiplied by X. So don't be confused. All what we are trying to say is that the area of this intensity is 1/2 times the base, which is the entire base here. Okay, and then it is what? Multiplied by the intensity. And that this time, because you have taken a portion, so this is the intensity of the portion. I hope it makes sense right now. Good. So at this juncture, what we are going to do is straightforward, because we took a section. Okay, therefore shear force is going to come down by convention, and then moment is going to come here. The question is, we are interested in this bending moment. Okay, this is the moment that we are interested in, and this is what we are interested in finding the algebraic expression for. You see that if you read the question, it said we should come up with what? An algebraic expression, and that is the algebraic expression. Okay, so all what we are coming to do right now is to find an expression for mx. So we are going to sum moment about section x. Clockwise is positive, should be equal to 0. In other words, this whole member is in what? Equilibrium. Let's quickly do that one. So if we do that quickly, first of all, we have W naught L over 2. That is the reaction force. The distance is what? X. Okay, the distance is X. That is it. And then don't forget that already this is a moment on its own. Okay, it is a moment on its own. So, but then it's anti-clockwise. So minus W naught L squared divided by 3. Right. And then what else? You realize that this load here, so what is it? This load is going to cause counterclockwise. So minus 1/2 W naught over L. Sorry, W naught over L x squared. That's this load here. And then the moment that is going to cause is actually a distance of what? X over 3. Okay, so that is it. Now, the mx is itself the moment that we are looking for, but then it is also what? Counterclockwise. Can you see that? So it's going to be what? Negated. So minus what? Mx. Right. So actually that is it. So we can go ahead and find mx. So mx, which we are interested in, is what? So this one, the strength of materials has ended. It's just a matter of what? Algebra. Okay, this is just algebra. Just make sure that you are able to express it well. So if we do the expression correct, then we have W naught over W naught L2, we have X, and then we have what? We have W naught L squared over 3, and then we have what? W naught over 6L, and then what? X cubed. S squared minus S squared times X is what? X cubed. So in fact, this is the expression. So if you're able to do up to this point, then it means you understand the course, because you have been able to do everything at least up to this point. Okay, but interestingly, this is where the actual solution to the question begins, because if you are not able to solve for the moment, you cannot solve the question. And if you get this wrong, it means the whole thing is wrong. All right. So this is kind of interesting. I hope you're happy you are able to do up to this point. Right. Okay, so actually we've now been able to get the moment. Okay, so now that we have the moment as a function of x, let's try and put everything together. Okay, so if you look at the question, W naught was given us what? So W naught was given us okay, so looking at the question, W naught was given us 100 kilonewton here, 100 kilonewton meter or per meter. So we can see that 100 times 10 to the power 3 all divided by 2. The length was what? L was 10, right? We can check it. The length was given as 10. Now we will come down here and then we just write x, then minus again 100,000 10 to the power 3 and then we have, so we divide here by 3 and then we multiply by the length squared, which is 10 squared, again minus 100 times 10 to the power 3, then we divide here by 6, multiply by the length, and the length was what? 10, and the s cube, of course. So actually this is the moment function. So if you do everything correct, let's try to bring this one down. So it's actually going to be 100 multiplied by 10 to the power 3, and then here will be divided by 2, and then multiply by 10. So that is like 500,000 x. So 500,000 x minus what? Let's do the s cube. So we have right. So we have 100 times 10 to the power 3 divided by 6 multiplied by 10. So 1666.667 x cube. And then finally, the constant, which is what? So we have, where is it? Yeah. So we have 100 times 10 raised to the power 3 divided by 3 multiplied by what? 10 squared. So that is it. We get 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7 multiplied by 3. So actually this is what you are going to get. Now at this point in time, you have gotten the moment function. It means that we can equate, from the differential equation of the beam deflection is just going to be this. Okay, so this means that EI d squared y dx squared is just simply going to be what? It's just simply going to be so everything here. So 500,000 x minus 166.67 x cubed minus what? 1, 2, 3, 4, 5, 6, 7, 3, 3. So that is it. Let me bring it down here. So 1, 2, 3, 4, 5, 6, 7 point what? 0.33. Right. So actually, this is the starting point. So let's integrate to get the slope. To get the slope, it's actually going to be 500,000 x squared all divided by 2 minus 166.67 x4 all divided by 4 minus what? 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, 7. Point what? 33. Now of course, integrate, so x comes here again, right? So yeah, and then what? Plus what? C1. Right. So this is actually the slope equation. So you have EI dy dx should be equal to what? 500,000 divided by 2 will be what? 250,000. No two ways about that. Squared. Right? Minus what? So let's do this one. 1666.67 divided by 4. And that's 416.6675. 416.6 so 0.6675 x to the power 4 minus 3, so 1, 2, 3, 4, 5, 6, 7.33 x plus C1. Now to find C1, we have to understand that from the boundary conditions all the time for a cantilever beam at the free end, at the fixed end at x equals 0, the slope is always 0. Okay, so if you put x equals 0, dy ds is 0, you realize that everything will be 0. So 0 equals 0, 0 plus C1, meaning C1 is 0. So C1 is 0, okay? So you have dy dx to be equal to what? 250,000 x squared minus what? 416.6675 x4 minus 1, 2, 3, 4, 5, 6, 7.33 x. C1 is 0. So now if you want to find the maximum slope at dy dx maximum, that is the free end, x equals L. So where you see x, put L there, which is what? 10. Okay, put 10 there, which means the maximum slope, so dy dx is going to be what? 200 and is going to be 250,000 multiplied by x squared, and x is this time 10 squared minus what? 416.6675 10 to the power 4 minus what? 1, 2, 3, 4, 5, 6, 7.33, and the x there is 10. Okay, so yeah, That is it. And then you divide everything by the EI. And then you realize that the E was giving us 200 gigapascal. So 200 times 10 to the power 9. And then the I was, so everything is here. 200 gigapascal, and the I was 120 times 10 to the power 6 millimeters to the power 4. So it's actually 120 times 10 to the power 6 millimeters to the power 4. So 10 minus 3, which is milli to the power 4. Now, this will be your maximum slope, okay? This will be your maximum slope. And let's pick our calculator and quickly do that. So I want you to do this on your own. I'm going to give you the answer straight away. So use your calculator to convince yourself. Okay, so the maximum slope is going to be minus 0.520 in radians. So if you want to get the maximum deflection, you follow the same principle, but then you have to actually integrate. So you have to integrate the slope equation. Sorry, you have to integrate. Yeah, you have to integrate the slope equation in order to get what? The deflection. Let's do that quickly. We are about to integrate. So maybe let me copy it. So we want to integrate. I'm sorry. Okay. Okay, so we want to integrate this, and we are saying that it's just going to be okay, so we are going to integrate it. It's going to be, we have EI sorry about that. So if we integrate, with respect to x, then we have EI y equals what? 250,000 x cubed over 3 minus 416.6675, then divided by 5, because this will be x5, then minus 3, so it's 7. 1, 2, 3, 4, 5, 6, 7. 0.33 x squared over 2 plus C2 plus C2. Okay, so this was the continuation of what is there. Right. Now, if you look at it carefully, all the time also, for a cantilever beam at x equals 0, the slope is 0, the deflection is also 0. So y is also 0. So without wasting much time, C2 is also 0. Okay, C2 is also 0. So we can confidently say that EIY is equal to what? So 250,000 divided by 3. So we have 250,000 divided by 3, multiplying what? Oh, sorry. So 250,000 divided by 3, which is 83. So we have 83.33 x cubed minus 416.6675 divided by 5. 83.335. 83.3335 x5, and then minus, so 333, 1 2 3 4 5, 1 2 3 4 5 6 7 divided by 2, which is what? 1, and the 6 is 1 2 3 4 5 6 7. So 1 2 3 4 5 6 7 point what? 5 x squared. Okay, so as a matter of fact, I will not do this. What I want you to do is that at x equals L, which is at x equals 10, that is where the deflection is maximum. So just put 10 here and divide by EI and tell me the answer. Don't forget that the E is 200 times 10 to the power 9. And then the I is actually, I think it's, so the I is what? 120 times 10 to the power 6. Okay. So the I is 120 times 10 to the power 6 times 10 to the power minus 3 to the power 4 because of millimeters to the power 4. So guys, what is Y max? Put it in the comment section below. Thank you very much for watching.